I have to admit, I fell down a rabbit hole last night.
Oh, yeah.
I was trying to get ChatGPT to help me plan a complex travel itinerary. Flights, hotels, dinner reservations, checking weather, the whole 9 yards.
The classic stress test. How did it go?
Well, for the first 2 prompts, it was amazing. But about 4 prompts in, it completely lost the plot.
Okay, I think I know where this is going.
It forgot the dates, it tried to book a hotel in a city I wasn't even visiting, and then eventually it just started hallucinating flight numbers, like completely made-up ones.
It sounds like you hit the wall, that invisible ceiling where the lone genius model just falls apart.
That's exactly what it felt like, and it's funny because we spend so much time obsessing over the model itself, right?
Yeah.
Like, oh, look how smart GPT-4 is, or look at the benchmarks on this new open-source model. We treat them like these singular all-knowing oracles.
We really do. But the source material we're diving into today, this technical notebook on architectures of agent orchestration and memory systems, it basically says we're looking at the problem through a straw.
Through a straw, yeah. We're missing the big picture.
We really are.
Yeah.
If you look at where the actual, the real engineering is happening right now, it's not just about making the chatbot smarter. It's about making the system work.
The system, not just the brain.
Exactly. The source makes a really provocative point right off the bat. The revolution isn't the AI model. The revolution is the digital workforce.
Digital workforce? That sounds a lot more intense than just a better chatbot.
It is. Think about your travel problem. You didn't need a poet or a philosopher. You needed a team.
I needed a travel agent, a scheduler, a researcher.
And a negotiator, all working together. You needed an office full of specialists. And that is what this agentic architecture is all about.
So, moving beyond just talking to one thing.
It's about moving from a single prompt, please do this, to a complex system that can organize, think, remember, and crucially, correct itself.
So we're unpacking the invisible plumbing today, the stuff that happens behind the chat window.
Exactly. We're going to look at the hidden architecture. The source breaks this down into 3 massive categories that I think are, well, they're just fascinating.
Okay, lay them out for me.
First, there's orchestration, which is basically the org chart. How do you get a bunch of AI agents to work together without, killing each other?
Okay, the org chart. I like that. What's next?
Then there's control flow.
Yeah.
That's about how an individual agent actually thinks through a problem step by step. It's the internal monologue.
It's operating system.
It's operating system. Perfect. And finally, the big one, memory. How do we fix the amnesia problem so these things can actually learn from experience?
I love that framing. The org chart, the operating system, and the brain.
It's the best way to visualize it.
Yeah.
Because right now, single agents are fragile. They are powerful, yes, but fragile.
They get stuck. They hallucinate, like my travel planner did.
Exactly. And if you want to build software that can actually run a business process, it's something that takes days to run, not seconds, you can't rely on a single smart model. You need an architecture that is resilient.
A system that can recover when things go wrong.
Yes. That's the whole game.
Well, let's start with the structure there, the org chart. The source calls this section coordination paradigms, which sounds incredibly corporate, by the way.
It is a bit jargon heavy, but the concepts are actually very intuitive. It's basically just asking the question, who reports to whom?
So if you have 5 different AI agents trying to solve a problem, what's the network topology? Who's in charge?
Precisely.
The first one they mentioned seems like the default for most people, the hierarchical model.
Right. And this is the supervisor-worker model.
Yeah.
And honestly, it mimics the traditional corporate structure almost perfectly.
So we have a boss, an AI boss.
You have a boss. You have a supervisor agent. And this is usually running on a really high-end model, like GPT-4 or Claude 3 Opus, a model that can do complex reasoning.
And it doesn't do the actual work itself.
No, the supervisor doesn't do the grunt work. Its entire job is to understand the user's high-level goal. Say, build me a website, and then break that goal down into concrete subtasks.
Okay, so the supervisor thinks, to build a website, I need code, I need design, and I need copy.
Exactly. And then it hands those tasks off to specialized worker agents.
So it's a dispatcher.
It's a project manager. You might have a coder agent that is optimized for Python or HTML. You might have a copywriter agent that's been fine-tuned on marketing text. The supervisor assigns the work, the workers go off and do it, and then they report back.
This feels very safe. It's logical, it's clean. You know exactly who is responsible for what.
That's the biggest pro of this system. It's incredibly clear. If the code comes back broken, you know exactly who to blame, the coder agent.
You can pinpoint the failure.
And the supervisor can actually review the work. The source mentions that in systems like OpenAI Swarm or Microsoft's AutoGen, specifically with its group chat manager,
Yeah.
the supervisor can look at the output and say, no, this is wrong. Do it again.
Wait, it can essentially reject the work, like a manager giving feedback.
Yes, it acts as a quality control gate. It can provide specific feedback, like this code doesn't handle edge cases, and then it loops the worker agent until the output meets the standard.
That sounds great for reliability, but I'm sensing a but coming. Because in the real world, having a micromanaging boss isn't always the most efficient way to get things done.
You nailed it. There is a massive, massive bottleneck here. The supervisor is a single point of failure.
Ah, okay.
Think about it. Every single decision, every piece of completed work has to go back up to the boss for approval. It creates a traffic jam.
So if the supervisor gets confused or goes off track,
The whole company shuts down. Or worse, if the supervisor hallucinates, if it gives the wrong instructions,
Right.
then all the specialized workers just create garbage with extreme efficiency.
right, the workers are only as smart as the instructions they receive.
Exactly. And there's a serious latency cost, too. You're paying for the supervisor's thinking time constantly.
Mhm.
It's not just one call to a big model. It's supervisor thinks about X, assigns X, waits for X, reviews X, provides feedback on X.
It's a whole conversation, and each turn costs money and time.
It's the bureaucracy of AI.
So it's safe, it's predictable, but it's slow and brittle.
If the head is cut off, the body dies. That's the summary.
So naturally, the engineers looked at this and said, let's kill the boss.
Let's flatten the org chart.
And that brings us to the second paradigm, the network or swarm. The source describes this as a peer-to-peer structure.
This is a totally different beast. In a
Right.
swarm, there is no designated leader. There's no supervisor. All the agents are effectively peers, sitting around a table.
So how on earth do they decide who does what? Do they just shout at each other?
Kind of. In a way, yes. They broadcast messages to the group, or they negotiate directly based on their system prompts and capabilities.
Okay, so give me an example.
Imagine you throw a problem into the middle of the table. We need to research this new medical paper and summarize its findings. You might have a biologist agent, a chemist agent, and a data analyst agent sitting there.
And they just figure it out themselves.
Right. The biologist agent might broadcast, I recognize these biological terms. I'll take the abstract and methodology sections. The data analyst agent says, I see a table of numbers with p-values. I'll parse that and run a statistical check.
So they self-assign tasks based on their skills?
Yes, and they can hand tasks back and forth dynamically. The analyst might say, hey, chemist agent, I've extracted the molecule data. Does this make sense to you? And the chemist can validate it.
That sounds incredibly resilient. If the biologist agent crashes, the others can maybe pick up the slack, or at least the whole system doesn't instantly die.
It's very resilient. That's the primary benefit. And it's much more scalable. You can add new agents with new skills to the room without rewriting the whole management structure.
Okay, but this sounds like it could get chaotic.
It does. This total freedom creates a very specific and honestly a quite funny problem.
The chatter problem? I saw this in the notes and I laughed out loud.
It is objectively funny until you see the bill for your API calls.
Right.
Because there is no boss to step in and say, okay, enough talk, get back to work. These agents can get stuck in social loops. The source specifically mentions infinite loops of politeness.
Wait, like, actually, after you? No, I insist after you.
Literally that. Large language models are trained to be helpful and polite. So you might have Agent A say, here is the data you requested. And Agent B says, thank you, that is excellent and very helpful.
Oh, no.
And Agent A replies, you're most welcome, I'm glad I could assist. Let me know if you need anything else. And Agent B says, I appreciate that, thank you again. And they just keep going.
And meanwhile, every single one of those words is a token that you're paying for.
Exactly. You are burning tokens. You are paying for computing power to watch two robots have a tea party.
That is the most expensive tea party in history.
And it's not just politeness. They can also get into disagreement loops.
Okay, so they'll argue.
Endlessly. One agent might say, based on my sources, the answer is 5. Another says, well, my tool says the answer is 6, and they go back and forth. But my calculation says 5, but my source says 6.
Without a supervisor to step in and be the tiebreaker?
Exactly. Without a manager to say the answer is 5, document the discrepancy and move on, they can argue until the context window runs out or you hit your budget limit.
I can imagine debugging this is an absolute nightmare. In the hierarchy model, if something breaks, you check the boss's logic. In a swarm, who do you even blame?
That's the other major downside. The source notes that debugging a decentralized graph is exponentially harder. You have to trace the conversation thread through every single agent.
It's like trying to figure out how a rumor started in a high school cafeteria.
That's a perfect analogy. Everyone said something, but pinpointing exactly where the logic broke or where the bad information came from is incredibly difficult.
So we have the dictatorship, which is slow but clear. And we have the anarchy, which is fast and resilient, but chaotic and expensive.
That's a good summary.
Then the source pivots to something that sounds a lot more industrial, MapReduce.
Yeah, MapReduce is a classic computer science concept borrowed directly from the world of big data processing. It's not really about conversation or negotiation at all. It's about raw throughput,
It's an assembly
a
line.
massively parallel one, yes.
The notebook used the S&P 500 as an example here. Can we walk through that? Because I think that really helps clarify why you'd use this instead of a swarm.
Definitely, it's a perfect use case. So imagine your task is, read the quarterly earnings report for every single company in the S&P 500 and tell me which ones mention AI in a positive context.
Okay, that's 500 reports. Each one is probably, 50 pages of dense financial text. If I ask a single agent to do that, it'll choke.
It will absolutely choke. It will run out of memory. It will take 3 days. And by the time it gets to the company starting with Z, it will have completely forgotten or hallucinated the results for A.
So how does MapReduce handle it?
It uses what's called a fan-out, fan-in architecture. First, you have an orchestrator agent that fans out. It takes that list of 500 companies and spawns 500 individual identical tasks.
So it creates 500 little worker agents just for this job.
Essentially, yes. Or 500 parallel function calls. And here's the key. They all run at the same time.
Parallel processing.
That's the magic. Agent number 1 looks at Apple. Agent number 2 looks at Microsoft. Agent 499 looks at Zimmer Biomet. They don't talk to each other. They don't know the others exist. They just do their one tiny job.
And that's the map part of the name, right? Mapping the same function across a list of inputs.
Precisely. It's all about speed and scale. Then once they're all done, you fan in. The orchestrator collects all 500 summaries. Apple, yes, positive sentiment. Microsoft, yes. Zimmer, no mention. And then it reduces them into one single final report.
So it's an assembly line, but instead of one station after another in a sequence, it's 500 stations running simultaneously.
Exactly. It's the industrialization of reasoning.
Yeah.
You would never use this to write a novel because a novel needs continuity and shared context from chapter to chapter.
Right.
But for research, data extraction, or any problem where you can split the work into little independent chunks, nothing beats the speed of MapReduce.
It seems like the trade-off here is context. The agent looking at Apple's report doesn't know what the agent looking at Microsoft's report found, so you can't spot trends across the data while the process is running.
Exactly. That synthesis, that higher level understanding, only happens at the very end in the reduce step. So if you need real-time collaboration or for one agent's output to influence another's input, this is the wrong tool. But if you just need to process a mountain of text in 5 minutes, it's the only tool.
Okay, that makes sense. There was one more paradigm mentioned, and honestly, I struggled to differentiate it from the others at first. Choreography. How is this different from orchestration? They sound like synonyms.
It's a subtle distinction, but a critical one for engineers. Orchestration, like we said with the hierarchy, implies a central conductor.
The boss.
The boss, the supervisor. There is a brain explicitly telling the other agents what to do, when to do it, and who to pass their work to next.
Okay, a central controller.
Choreography is different. It's about a set of pre-agreed rules that everyone follows independently. There's no central conductor telling them the rules during the performance. The source used a traffic analogy that I thought was brilliant.
Yeah, the traffic light versus the traffic circle. That really clicked for me.
Exactly. Think of orchestration as a traffic light. The light is a central controller. It is the boss of the intersection. It turns red, you stop. It turns green, you go.
And if the power goes out?
If the power goes out and the light turns off, the intersection becomes a disaster zone. The system fails because the central controller failed.
Okay, and choreography is the roundabout.
Yes. In a roundabout or a traffic circle, there is no central controller. No one's telling you when to go. But there is a rule, a simple baked-in rule. Yield to traffic already in the circle.
Right. Everyone knows the rule.
Every driver knows the rule, and they interact with each other based on that shared protocol. The system works without a boss.
So in the AI world, this would be hard-coded rules for interaction.
Exactly. It's a script or a protocol. For example, you might program a system where the writer agent always passes its completed draft to the editor agent. The writer doesn't need a boss to tell it that. It's just the law of this particular system. I am the writer, I'm finished, therefore I hand off to the editor.
I see. So it removes the single point of failure of the boss, but it also removes the chaos of the swarm because the interactions are predefined and not negotiated.
It's very robust for well-defined processes. But the downside, a lack of flexibility.
Ah, of course.
If you want to change the process, say you want to add a fact-checker agent between the writer and the editor, you can't just tell the boss, hey, change the plan. You have to go in and rewrite the core code for the writer and editor agents. You have to fundamentally change the choreography.
So, to recap the org chart, we have the hierarchy, which is command and control. We have the swarm, the Wild West. MacReduce is the factory floor, and choreography is the rulebook.
That's a great way to put it.
It seems like building the right agent system is mostly about picking which of these management styles fits your specific problem.
That's the job of the AI engineer now. It's not prompt engineering anymore. It's organization design. You are literally designing a company made of software.
Okay, so we've built the office, we've hired the staff and given them a management structure, but now we need to look inside their heads.
Right.
How does a single agent actually function? The source calls this control flow.
This is the agent's internal operating system.
Right.
We're moving from how do they talk to each other
Mm-hmm.
to the more fundamental question of how does one agent think?
And the first acronym here is one I've seen floating around everywhere, REACT.
React.
Yeah.
It stands for reasoning and acting.
Mm-hmm.
It is, you could say, the grandfather of modern agentic workflows. It's the foundational loop that really made agents possible in the first place.
Okay, so how does it work, fundamentally?
It's a surprisingly simple loop of 4 steps: thought, action, observation, and then repeat.
Okay, walk me through a real example. Not just what is the weather, but something a bit messier that requires a few steps.
Good idea. Let's say you ask a React agent, find out who the CEO of company X is, and then find their email and draft a sales pitch to them.
The classic multi-step sales test.
Exactly. So step 1 is thought. The model thinks to itself internally, okay, the user wants me to email the CEO. First, I need to find the CEO's name. I don't know it. I should use a search tool.
So it formulates a plan.
A very small one-step plan. Step 2 is action. Based on that thought, it constructs a tool call, something like search Google company X CEO. It executes that action.
And then it waits.
It waits. And then step 3, observation happens. This is crucial. The tool runs and brings back text from the real world. Maybe the search result says Jane Doe was appointed CEO in January 2024.
Okay, so now it has a new piece of information.
Right. So it loops back to the start. Step 4 is repeat thought. The agent reads that observation from the tool and updates its internal state. It thinks, okay, I know the name is Jane Doe. Now we need her email address. I should search for that.
So it goes through the loop again.
Yes. New thought. Search for Jane Doe's email. New action. Search tool. Jane Doe email address. New observation. Maybe this time the tool comes back with no results found.
Ah, a dead end. So what happens then?
This is where React shines. It doesn't just give up. It reasons again. Its next thought might be, okay, a direct search failed. I should try to guess the common email format for that company, like jane.doe@company.com, or I could search for the company's general contact page.
So it adapts, it sees the failure from the observation step and tries a new angle based on that.
Exactly. That observation step effectively gives the AI eyes and ears. It allows it to react, pun intended, to the real world and not just follow a rigid script.
But, and there's a but, right? This process sounds excruciatingly slow.
It is so slow
Yeah.
and expensive.
Because it's stopping to think after every single tiny action.
It stops, it generates a thought, which is a call to the LLM. It calls a tool. It waits for the tool to finish. It reads the output. And then it calls the LLM again for the next thought. It's taking tiny baby steps.
And each of those thought steps is an API call you're paying for.
Yes. For a complex task, a React agent might take 50 or 60 steps, meaning 50 or 60 calls to GPT-4 to do what a human would do in 2 minutes of Googling.
It feels a bit like watching someone type with 2 fingers. It works eventually, but you just want to grab the keyboard and do it for them.
That is the perfect analogy. So to speed things up and add more structure, the source introduces the next evolution, LangGraph.
This was described as a state machine. Now, I'm not a computer scientist, so explain that to me like I'm 5, or maybe 12.
Think of React as a stream of consciousness. It just goes wherever its thoughts take it next. LangGraph is a flowchart.
Okay, flowcharts I can do, boxes and arrows.
Right. In LangGraph, the agents or functions are the nodes, the boxes, and the logic that connects them are the edges, the arrows. You explicitly define the path the logic can take.
But what makes that different from just, a regular computer program?
The superpower that makes LangGraph different is that it allows for cycles.
Loops. You mean it can go backwards?
It can go backwards. Traditional code, especially in workflow systems called DAGs, or directed acyclic graphs, is designed to go one way, start middle end, maybe with some branches, but it always moves forward. LangGraph lets you draw an arrow that goes back to a previous step.
Why is that such a big deal?
Think about a common real-world process, like writing code. You write the code.
Yeah.
Then you test the code. If the test fails, what do?
You go back and you fix the code.
You loop back. In LangGraph, you can explicitly build that structure. You have a coder node and a tester node. The array goes from coder to tester.
Yeah.
The tester runs the code. If it returns an error message, you define an edge, an arrow that points back to the coder node, and it passes the error message along.
Error on line 5.
Exactly. The coder gets that as input, tries to fix it, and sends the new version back to the tester. If the tester says success, then a different arrow points forward to the deploy node.
So it creates a self-healing loop, but a very structured one.
A very structured, very controllable one. You can define strict business logic. Do not proceed until this test passes. Try up to 5 times. If it fails 5 times, escalate to a human. You can't do that reliably with a fuzzy, open-ended React loop. LangGraph gives you engineering control over the AI's workflow.
That makes a ton of sense. It's professionalizing the process. But there is one concept in this section that really stuck with me because it sounded almost like magic. Durable execution.
Yes.
The source called it the invincible agent.
This solves the most boring but most dangerous problem in AI automation, the server crash.
We've all been there. You're downloading a huge file or you're rendering a video and your laptop battery dies or the Wi-Fi cuts out.
Yeah.
And you lose everything. You have to start from scratch.
Now imagine that on an enterprise scale. You have an AI agent that's running a process that takes 3 days. Maybe it's processing 1 million invoices. On day 2, at invoice 600,000, the server it's running on needs to be restarted for a security patch.
The agent dies. The memory is gone. The process is lost.
And when you restart the system, the agent starts from 0. It might try to reprocess those first 600,000 invoices, creating duplicates. It's a disaster for any long-running or mission-critical task.
So how does durable execution fix it? The source mentions systems like temporal and restate.
They use a clever technique called event sourcing. Basically, the agent writes a diary entry to a persistent database before and after every single tiny step it takes.
Every single one.
Everyone. It writes, I'm about to check the customer's account balance. Save to database. Then it runs the check. Then it writes, I checked the balance. It is $50.32. Saved to database. Then it writes, I am about to initiate the transfer. Saved.
So if the server catches fire right at that moment...
When you plug in a new server and the system reboots, the agent wakes up. It reads its diary. It sees, oh, I already checked the balance. I was just about to initiate the transfer. And it resumes exactly where it left off at that precise step.
It's like a video game save point, but it auto-saves after every single pixel of movement.
That's a great way to think about it. It's an invincible zombie agent. You can kill the hardware, but the state of the process cannot be killed.
Yeah.
For companies putting AI into real production, where real money is moving, this isn't optional, it's mandatory.
That is fascinating. It's taking the flakiness out of AI.
Oh.
Okay, one last control flow method before we move on to memory. Re-woo-woo.
Re-woo-woo.
Reasoning without observation. This one sounded like a shortcut, an optimization.
It is an optimization. A very clever one. Remember how we said React is slow because it stops and looks after every single step?
Right. Step, think, look, step, think, look.
ReW says, what if we can plan the whole thing up front? The agent looks at the user's request and writes a full plan immediately, but it uses placeholders for the data it doesn't have yet.
Placeholders? What do you mean?
Okay, let's say the task is, what is the ratio of France's GDP to Germany's GDP? A React agent would do this in several steps. ReWO does it differently. It generates a plan that looks like this.
Use the search tool to find GDP of France. Call the output of this result.
Use the search tool to find GDP of Germany. Call this result 2.
Use the calculator tool to compute result none divided by result 2.
I see. It doesn't know the numbers yet, but it knows the algebra. It
Right.
writes the whole equation before it has the variables.
Precisely. And this is brilliant because now the execution engine can see that step 1 and step 2 don't depend on each other, so it can run them at the same time.
In parallel.
in parallel. And more importantly, it decouples the reasoning, the smart, slow, expensive LLM part that makes the plan from the execution, the dumb, fast, cheap tool part that just fills in the blanks.
So the brain says, here's the plan, go do it, and then it can basically go to sleep, and the hands go do the work.
And then the brain just wakes up at the very end to put it all together.
Right.
It's vastly more efficient for any task where you don't need to see the result of step one to know what you need to do in step two.
It's separating the architect from the construction crew.
That's a perfect analogy.
Okay, so we've got the team structure with orchestration.
Yeah.
We've got the internal workflow logic with control flow. But we have a major fundamental problem left to solve: amnesia.
The big one.
Large language models have the memory span of a goldfish. Actually, that's an insult to goldfish. They have no memory whatsoever.
They are stateless functions. It's a core concept people often miss. Every time you send a message to ChatGPT, it is effectively meeting you for the first time.
And the only reason it remembers your previous message is because the app is silently resending the whole conversation history back to the model every single time.
Exactly. And that trick works fine for a short chat. But if I want an AI employee that works with me for a year, pasting the entire year's history into the prompt is impossible.
It won't fit in the context window, and even if it did, it would cost a fortune in tokens.
Precisely. So we have to engineer a brain. We have to build an external memory system. The source outlines 5 different types of memory systems that developers are building right now.
Okay, let's go through them. The first one is the most basic, working memory.
This is the RAM. This is that immediate context window we were just talking about, the conversation you are having right now.
So its main characteristic is that it's high resolution.
High resolution, yes. The model knows exactly what you just said a second ago, but it is incredibly volatile. As soon as the session ends, or as soon as the text gets too long and scrolls out of the window, it's gone forever. It's a temporary scratch pad for immediate calculations.
Got it. Then we have episodic memory. This sounds personal.
It is. This is the agent's diary. Episodic memory is for storing structured logs of past event sequences. On Tuesday at 2 p.m., I tried to run this code and it failed with error X. Or on Wednesday, the user told me they prefer Python over JavaScript for new projects.
So it's a history of what happened.
A structured history. But the source emphasized a specific concept here that's built on top of this memory, called reflection. This seemed like the most important part of the entire memory section to me.
It's the holy grail of agentic AI right now. Reflection, and it's usually spelled with an X in the research papers, is the ability of the agent to look back at its own diary and critique itself. Wait, self-criticism. For real.
Yes. Without reflection, if an agent fails a task, it just fails. If you ask it to do the same task again, it might make the exact same mistake because it doesn't learn from failure.
It's just following its programming.
But with a reflection module, after a failure, the agent can pause. It can read its episodic memory log. I tried strategy A. It resulted in error Y. Therefore, strategy A is a bad approach for this type of problem. It writes that conclusion, that reflection, back into its memory.
So the next time it encounters a similar problem, it checks its diary first.
And it sees the note to self. Don't do strategy A, it learns. This feedback loop is what turns a static model into an improving system. It allows the agent to get smarter over time without OpenAI or Google having to release a new base model. It gets smarter through its own unique experience.
It is huge. That's the difference between a tool and a trainee. A trainee learns from their mistakes.
That's the goal.
Okay, next up is semantic memory. The source calls this the library.
You'll hear people in the industry call this RAG, which stands for Retrieval Augmented Generation. This memory type is for storing long-term static facts.
So not experiences, but knowledge.
Knowledge. If you want your agent to know the contents of your company handbook, or the entire U.S. tax code, or the complete history of ancient Rome, you put that information here.
And this uses a vector database, right? I always hear that term thrown around, but how does that actually work in simple terms?
Imagine a library with 1 billion books. The agent can't possibly read or carry them all in its working memory. A vector database is like a magic librarian. When the agent has a question like, what is our company's policy on remote work? It asks the magic librarian. The librarian doesn't read all billion books. It uses math vector embeddings to instantly find the specific paragraph on the specific page that is semantically close to the meaning of the question.
So it looks for meaning, not just keywords like a regular search.
Right. And it pulls just that one relevant chunk of text, hands it to the agent, and says, Here, read this into your working memory and use it to answer the question. It allows the agent to appear as if it knows everything, even though it only reads a tiny bit at a time, just in time.
The fourth type, procedural memory. The notebook calls it muscle memory.
This is for implicit knowledge. It's not facts like semantic memory, and it's not what happened yesterday like episodic memory. It's the how do I do this memory. It's about skills.
How do you store a skill in a database? That seems abstract.
Usually as a library of templates or what are called few-shot examples. Let's say you want an agent that is really, really good at writing SQL database queries in a specific dialect for your company. You don't just say write SQL. You store a library of 50 perfect examples of SQL queries that follow your company's style guide. When the agent needs to write a new query, it pulls a few of those examples into its context to remind itself of the correct syntax, formatting, and style.
It's like a chef looking at a recipe card. They already know how to cook, but they glance at the card to get the proportions and the steps exactly right for this specific dish.
Exactly. It isn't learning a new fact, it's recalling a process. It stabilizes the output and ensures consistency.
Now we get to the final memory type, and I have to be honest, this one made me raise an eyebrow when I read it, the emotional bank.
The wild card.
The source specifically references a framework called VGL that uses this concept. Why on earth does a software program need an emotional bank?
It does sound like we're drifting into science fiction or maybe a Black Mirror episode.
Yeah.
But technically, this isn't about the AI feeling sad or happy. It's about data compression and prioritization.
Okay, explain that. How does emotion lead to compression?
Think about your own human memory. Do you remember what you had for lunch on a random Tuesday 3 years ago?
No, of course not. No clue.
But do you remember your wedding day? Or the day you broke your arm? Or a major career success?
Vividly. Every detail.
Why? Because those events had high emotional significance. Your brain uses emotion as a tag, as a filter, to decide what information is important enough to keep and what can be safely deleted. We can't store everything. It's metabolically too expensive.
So the emo bank is just a prioritization algorithm with a fancy name.
Essentially, yes. The system assigns a weight and emotional score to memories as they are stored. If the agent makes a catastrophic error that crashes the production database, that episodic memory gets tagged with a massive fear or severity weight of, say, 10 out of 10.
And it stamps it. Do not forget this, ever.
Precisely. But if it just has a mundane interaction, like saying hello to a user,
Yeah.
that gets a weight of 1 out of 10.
Okay, so it has weighted memories. How does that help?
Because the source also discusses the concept of the forgetting curve. Memories need to decay over time. If they don't, the database fills up with useless junk. By using this emotional weighting, the memories with a low score fade away quickly, while the high-impact memories are reinforced and retained for a long time.
It mimics the human ability to retain wisdom while discarding noise.
It's not about giving the robot a soul, it's about giving it a file dilution policy that actually makes sense for long-term learning and survival.
Wow. Okay, so let's step back and look at the whole architecture, the whole picture.
Let's do it.
We have the org chart, the orchestration layer, that decides if we're building a top-down hierarchy or a chaotic swarm.
The management stack.
We have the control flow, the operating system, that decides if an agent is improvising with React or following a strict flowchart with LangGraph.
The internal thought process.
And then we have the memory architecture, the brain, that uses episodic memory to learn from the past and an emo bank to decide what's important enough to keep. When you put these three layers together, what are we actually looking at? What have we built?
We are looking at the concrete transition from tools to systems. We are moving away from the era where you are the pilot and the AI is the co-pilot.
What are we moving to?
We are entering the era where you are the architect and the AI is the organization you've designed.
That is a massive shift in mindset. We aren't just coding software anymore.
We are architecting cognitive systems. We are building digital employees. And just like human employees, they need management structures, they need training manuals and standard operating procedures, and they need to be able to learn from their mistakes without burning the building down.
And that leads to the thought I wanted to leave everyone with, because this is what stuck with me from the source. It talks about reflection and emotional banks. If we succeed in building these systems, truly succeed, systems that can remember their own past, prioritize their memories based on a learned sense of importance, and self-correct their own behavior without us intervening.
Which is the goal.
Where's the line?
That is the big question, isn't it?
Where is the line between a complex, autonomous workflow and a colleague?
It's getting blurrier every single day. When the system starts generating a report and says, I decided not to use strategy A because I remembered it failed 3 weeks ago on a similar task, and you never explicitly programmed that rule.
It just learned it.
It learned it. That
Yeah.
feels like more than just software. It feels like intelligence.
Feels like agency. Real agency. Something to think about the next time you're frustrated with a chatbot that can't plan your vacation. It might just need a better org chart.
And a diary.
That's it for this deep dive. Thanks for listening.
See you next time.